I'd like to introduce the idea of debugging. One of the things that we might try out with regard to debugging is to look beyond the information which I've already provided and have a look at what a Magritte pipe does. So if we load and attach Magritte, we can of course look at the contents of the function, the textual representation of what the function, how the function is written, by typing its name, in this case in backticks, because it's an operation. We turn on debugging by using the debug function. So we've turned on debugging, and when we run a very simple pipeline, then we first once again are presented with the verbatim text version of the function, and in RStudio we also get a panel showing where we are with a yellow colored bar, or with the green arrow. We get a traceback showing what it is that's being traced, and we get the arguments taken by the function. So the function takes, as we can see here, takes a left-hand side and a right-hand side. The right-hand side in this case is the final part, and the left-hand side are all of the other ones. And we then execute the elements in sequence. When one is debugging the first time, it's quite complicated to work out what's going on, but it's possible to examine what is actually going on by typing the names of the objects which appear inside the function, so that they're within the scope of the function. They can't be seen from outside, but when you turn on debugging you can see them from the inside, so that if we take the right hand sides, they are then cosine, exponent and sine. The left hand side, we press again to instantiate it, is the number 4, so that we then have chain parts which are showing what the chain parts are. We get the environment, the parent environment, and the pipes, and in this case all of the pipes are standard Magritte pipes. The Magritte package has other kinds of pipes as well. So if we then begin to step through, we can track what is going on. First we've applied to the length of 1 to the length of the right hand side, which is 3, wrapping the function of the pipes, so that that was this line. We've now gone on to attach their classes, and then we get to something which turns out to be interesting. Usually when you're debugging you don't see things the first time. I didn't see this the first or second or third times, but in the end I realized that freduce is probably important. This is coming from the names of MapReduce, so that map is to generate a list of, in this case, functions, and reduce, a function reduce, is to run through the functions in turn, passing through the left-hand side and right-hand side values. That the left-hand side value goes through the first one and becomes the result, which is moved back to the left-hand side and moves on from there. So what can we do about freduce? We could look at its help page, and there we see, yes, this function applies the first function to value, then the next function to the result of the previous function call, etc. So that it's freduce which is doing the work in this case. We can also turn on debugging inside debug, so that we can debug freduce and see what will happen when we get that far. And now we've moved further forward on the pipe. Is the left hand side a placeholder? No. So we're now going to evaluate the left-hand side in the parent environment, and this is then placed in the local environment, and then we're going to evaluate the quote of the backticked sequence of functions on the left-hand side. So applying the sequence of functions to the left-hand side, and what will then be going on in the environments can be, we can get towards it by looking at what these things are. Now, can we see what this is? No. Why? Because it's not where we are in the scope that we are, it's been put into the environment. So we need to say get, and it would then be double quotes underscore fsec, and we need to say that we're getting it from the environment in which it's been placed, and here we have it. This is the same as we could have seen on the right hand side here, so that we're then this is the sequence of functions. We could also check, just to keep ourselves sane, that the left hand side is as we expect it. So what is going to be going on now is that we're going to be dealing with the sequence of functions on the original left hand side, and the sequence of functions, although we can't see it in this line, and that was why I didn't realize that f-reduce was what was the underlying engine, is that as soon as we execute that line, this line here, we get placed into f-reduce. So we're in f-reduce the first time. The debugging level has moved from 1 would be the global environment, 2 is in the scope of the pipe, the third one is in the scope of f-reduce. And we're now inside f-reduce, so we can see what k is. K is 3, that would be what we would expect, and you can see that the environment here is the one which was within f-reduce, so that we could have chosen other environments, but this is the one where we're inside f-reduce. We've got a function list, a list of 3, k is 3, and the value at the moment is not exposed. We now go into a short for loop, which is the loop in the number of functions minus 1, so that it takes the all but last functions from the first to the penultimate function and executes them on value. Value on entry is 4, so you execute first the first function on, so we have a look and see what I is. Okay, we need to start the loop. I is 1, the value of the function list. So we're now inside the scope so that we can look at the value of the function. That's the cosine, so that's what we're going to do first. And if we say value is 4, but if we execute it, value is going to be the cosine of 4. If we then take the exponent, because we're now in I is now 2, the function list is or should be exponent, right? And if we then run that and we say value, that would then be the exponent of the cosine of 4. And now we've come out of the end of the for loop. K is 3. We're now at the final function in the function sequence is sine, the value we've seen, and if we execute it, then we can see that the value is 0.497. Okay, so we're leaving f-reduce, and we go back into the pipe itself, or the pipe function, and all we're doing now is saying giving the result if it's visible, and we've dropped back out. So we've gone from the global environment inside the pipe function and inside freduce, which was doing the work. We can undebug freduce. We can undebug the Magritte pipe. For comparison, let's have a look at another pipe, the dot pipe, which is in the wrapper package. It appears to be smaller, but what is different in this case is that it is recursive, in the sense that it runs through different levels in itself. We'll turn on debugging. We'll run this one and see where we go. So we have the left argument and the right argument. The right argument is the one on the end of the pipe. So that's the one which would be the enclosing, the one you apply to the penultimate value. So it then takes the left argument, the right argument are then substituted, putting them into the pipe impl function, and this is then the one which is doing the work. And in contrast to freduce, this is doing something like freduce. It's also dealing with the same kinds of issues. We won't debug pipe impl because it's quite long, as you can see. It simplifies because it's taking a large number of special cases, so that we can see what is happening inside. So that we've run through the debug level 2, debug level 3, and now we go to debug level 4 because we're stepping along the pipe. I believe that the value is stored in dot. Yes, we've now come 2 steps along it, so we've taken the cosine and the exponent of the cosine, and we will now complete exiting, and you can see that there's the same kinds of steps which are being run in the dot pipe and in the Magritte pipe. If you run benchmarking on a very simple pipeline like this, the dot pipe is substantially faster than the Magritte pipe, but when you're dealing with larger or vectorized objects, then the differences are trivial. The dot pipe exposes many of the features which are present in a way in which the authors of the wrapper package declare as being standard evaluation rather than non-standard evaluation, which would be the way in which the Magritte pipe is implemented. A final small point is to use the Bizarro pipe, where we can say that we take the pipe symbol that we're using and we exchange it for the right arrow assigned to a dot, semicolon, and we'll replace this one, and this one. We're not going to replace any of the others, and we'll see what happens with this. And we can run this. So we're getting the same. This is known as the Bizarro pipe because it's using purely standard evaluation, and it could also be written in the following way, so that we could do this. which is another way of evaluating what is going on, because at this point we could add steps like this to show us what the intermediate values are, so that this would be the poor man's debug, because it allows us to examine the intermediate values at each step of the pipeline. Okay, enough about debugging and pipes for the moment. I'm just using pipes as an example. In practice, many uses of debug are when something has come out of the application of somebody else's function that we don't know about. We don't know why things have come out of the function, and maybe we've made a mistake about, say, the class of an argument, or maybe we're unsure about one of the classes of one of the columns of our data frame, and using debug allows us to examine what's going on inside the running function. An alternative, of course, is to use traceback once an error has occurred. Once an error has occurred, then traceback will probably give us a good idea of where to look. But using debug allows us to check everything inside the running function, which is a way of grounding sanity, so that you can see what is actually going on, and you can try out alternative approaches internally within the running function. Debug has been around since forever.